So, good afternoon everyone. Today I would like to talk about the unique responses that can be observed in odd parity magnets. What do I mean by odd parity magnets? Like if you reverse the momentum, you get the spin polarization opposite in sign. That's all I mean by here what is odd parity wave magnets. So, we all already know the non-relativistic spin splitting within the collinear magnetic regime can observed only in ferromagnets, the conventional one, and the unconventional altermagnets. For the conventional ferromagnets, where we have the parallel spin ordering which gives a net magnetization in the system, and as a result we are getting yeah. So, yes. So, in the conventional ferromagnet we all know that there is an isotropic spin splitting between the spin up and spin down channel, whereas for altermagnets we can have alternating spin splitting between up and down spins. Like here what I show for the lowest order altermagnet which is D wave, and that has two nodal planes. This both has a common similarity, like for the ferromagnets it preserves parity and the time reversal is essentially broken. Like if we change the momentum, it is in same sign. Similarly here, if we reverse the momentum, it has the same sign of the spin. It leads to a compelling question, can we have an odd wave parity magnets? Of course, the answer is yes. From the exceptional talks of yesterday and today, we already know that, that is not a surprise. So, here I show the lowest order P wave magnets which has only one nodal surface. It can have P wave magnets without any nodal surface, but for this the interest of this talk I am sticking to the nodal P wave magnets which has only one nodal surface, that I show it here. So, what is here, like the parity or the inversion symmetry is broken for this kind of system, whereas the effective time reversal symmetry in the momentum space is preserved. To get this kind of magnets, what are my symmetric criteria if feasible? We already know these are feasible. So, what are the symmetric criteria here? Even we found some P wave magnetic candidates, are they at all useful for any spintronic applications or that are just for the fundamental interest? So, these are two primary questions that we answer in this talk. What are the symmetry criteria? We know from the detailed symmetry and spin symmetry analysis done by Libor in his two papers that collinear magnetic order can only enforce even parity. So, if we want some odd parity wave magnets, we need to go to non-collinear magnets. That is essentially the criteria. And Anna and Libor has done a detailed calculations and figured out the three essential symmetries that we need to have an odd parity wave magnet. The first, the real space inversion must be broken. Second, the product of inversion and time reversal must be broken, because otherwise the Kramer's degeneracy will not be lifted. And additionally, it preserves the tau t, like time reversal times translation symmetry to be preserved. For the interest of this talk, we will be restricting ourselves to the coplanar magnets. The non-collinear order can have non-coplanarity also, but we will be restricting ourselves to coplanar magnets. Why? The answer will come in the later part of the talk. That will and so, the nearest neighbor Kagome antiferromagnet we all know, in the classical solution it stabilizes the 120 degree order, because if we want to populate it, the triangular network with collinear spins, it gives the frustration. So, to release the frustration, it stabilizes the 120 degree order, that we see it here. Like this triangular network, the spins are aligned 120 degree order. The all out configuration at the same point of time, all in 120 degree order is equally probable. But this magnetic configuration preserves the inversion symmetry. So, to satisfy the criteria of the P wave magnet, we tweak the magnetic ordering. How? We double the unit cell and we changed the magnetic order in such a manner like the two possible 120 degree orders all in and all out are nearest neighbor to each other. and as a result they are connected by tau T symmetry, which is another condition to have the p wave magnet. So let's see within this minimal model or minimal model magnetic configuration whether we are getting our expected result or not. Before doing any calculation, let's see what spin symmetry analysis gives us. Like that is necessary to have the exchange driven order where the spin orbit coupling is not there. There the spin symmetries are essentially coming into play. So we can break down our total Hamiltonian in the magnetic part where the exchange is there, and the relativistic part where the spin orbit coupling comes into play, which intertwines the spin and orbital moment. So we are basically the spin symmetry analyzes this H magnetic where we have a spin space symmetry operation where I have a real space symmetry operation that are decoupled essentially. So let's see what is there for this minimal model. So there are two parts, one is spin only group and another is non-trivial spin group. In the spin only group, it applies only to the spin space, like nothing is changing in the crystal space. So for this any coplanar system, nothing to do with only this 120-degree ordering. If we apply this coplanar symmetry, let's say we apply C2 perpendicular. Yeah, this 120-degree order is completely rotated 180 degree by the perpendicular axis, then application of tau essentially reduces to its original form. So this is other than the identity, there is C2 tau symmetry which is preserved in the spin only group. What gives us? This coplanarity symmetry suggests that if there is all three components of the spins, the outer plane spin component with momentum reversal changes the sign, whereas it does not change anything for the in plane component. So the antisymmetric nature of the outer plane spin component is there with this coplanarity symmetry. There are other symmetries like tau T, which is essentially a C2Z tau times half translation, which suggests that for each momentum the in plane component of the spin vanishes. For the simultaneous satisfaction of this two criteria suggests only the outer plane component survives and the in plane component vanishes. So this is essentially giving us the criteria like we are getting a complete pure P wave kind of nature with momentum reversal. There is only one spin component which is reversing the sign. So to solve this kind of magnetic ordering, we propose this Hamiltonian where the first term is capturing the local exchange field, where this J is not actually an degrees of freedom rather an parameter which captures this 120-degree ordering, and the next term is the usual tight binding hopping. And indeed we are getting, by solving this equation, the outer plane spin component survives, whereas the in plane spin components are essentially 0, that we expect actually from our spin symmetry analysis without doing any calculation. That follows in our calculation. So this is saying that time reversal symmetric band structure in our momentum space. So far so good. Within the minimal model level we are getting some P wave kind of characteristics. Can we have some candidate material for that? So our colleague Rodrigo has done a detailed calculation over the Magneta database, and he found essentially not one or two, rather 70 candidates which are P wave magnets till now. There are more to come, and among them 50 are coplanar which are of interest of this talk, and 20 are non-coplanar in nature. So we cherry picked one of the candidate. For this candidate the teaser has already been given by Daniel. This is one coplanar CNIASO coplanar P wave magnet where we have this half translation times C2Z symmetry like tau T symmetry, and this is actually experimentally synthesized by Hu et al. In 2019. Below 7 Kelvin, this stabilizes this non-collinear coplanar magnetic ordering. So we have written down in the same way like the minimal model what are the symmetry operators. We do not need the other operators, rather we will focus only this two. This is the coplanarity symmetry like the minimal model, and this is the tau T symmetry. and which gives us the time reversal symmetric but inversion broken p-wave nature of band structure. And it has a huge splitting which surpasses the like the values of yeah. Yes, sure.
So I just understand your notation. You say TA/2. Is it because you're considering the enlarged unit cell of the magnetically ordered phase?
So this is like the unit cell, and this is A direction. TA/2 means half translation along A.
Okay, but in terms of the original without the long range order, that would just be a regular translation.
Yes.
Is that correct?
So within the without the magnetic order, it's like the half of the unit cell. These two are there.
Okay.
It's just double.
Yeah.
Okay.
With magnetic ordering, it's just double. So there is a linear crossing at the gamma point, and it has a huge splitting that surpasses the like highest reported value till date for bismuth tellurium iodide. The bulk polar materials is around 100 MeV or so, and for our cherry picked material, it already surpasses that value. Now, we have already answered the question, what are the symmetry criteria? We have found some models, some like materials, but does that actually useful for any spintronics application? Let's answer this question. So yes, when we see for this candidate material of CNIASO, when we calculate the resistivity, they are different. How? Within the non-magnetic phase, there is this is your unit cell now. The non-magnetic unit cell is actually the half of the magnetic unit cell, and it preserves the C4Z symmetry. Like if you go x direction or y direction, if you see as an A and B, they are symmetric because of the C4Z symmetry, as we see in the band structure plot also. This is the energy surface cut for a fixed KZ plane. But when we go below the transition temperature, which is 7 Kelvin for this material, the Brillouin zone folds, and this C4Z symmetry is no longer there. As a result, when we go as an x-axis and y-axis, the dispersions are different, and we are getting different resistivity for these two perpendicular directions. Our calculations suggest around the Fermi energy, it's actually 15% for this material, and it can go up to 50% if we hold up it. So far reported, the relativistic AMR values can have till 1% of this resistive anisotropy, and our value is around the Fermi energy is 15%. And this is not only a theoretical prediction. I recently found out for our material CNIASO, there is an archive paper which suggests experimentally this is around 15%, and with magnetic field they can align the domains in some kind of way that can go up to 35%. And there are other experimental reports on similar P-wave materials, P-wave like materials, because they essentially for this candidate they break the time reversal in some sense, but P-wave like material to go up to 30 to 50% of the anisotropy.
If I didn't know anything about spin, I would say that's enigmatic. That's precisely the order parameter that the phenomenological order parameter for nematicity. The anisotropy in the resistivity tensor.
Yeah, that's good.
Yeah.
That would not distinguish the two. The other effect that she's about to show would distinguish it.
Okay.
Yes.
The Edelstein effect that is coming with it.
Okay.
It's clear that it's there because you can also see the strap face essentially there.
Okay.
The
Yes.
strap face
This
is
is-
there as well.
Right.
So that's not distinguishing from one from the other, but the
Correct.
Edelstein will.
Okay.
Yeah.
But this experiment essentially doesn't distinguish that.
But if you didn't have it, then it would be a problem. How's that?
So I have a question on this domain alignment. I mean, 35% is not that high, right? So and there are techniques to make, in fact, monodomains, and they are very well known in the iron-based community because this is what they have been trying for a long time. Is this really the best that one can do so far, or is just that you right now These are the
This
latest.
is so far reported after.
Ah, okay,
Yeah.
because
We're not in contact with them at all.
okay,
Yeah.
because there are
This is just
in
this
fact-
month.
We have no idea of what they did or how they did it.
Okay, because this.
This-
Yeah, I mean,
Layer,
Yeah, this is one plane what I am showing, and there are another plane.
the order is
but then the
what we
in-plane
call the
magnetic field
striforda.
breaks the symmetry. You don't need spins for that. Okay?
So yeah, so I think just for what Rosario is saying is that when they try to apply in-plane field to between the sample in nuclides, it was very, very hard. You need very large fields. But the moment they use just the strain cells, they would get a single domain. And so I'm sure that there are people that can do this experiment very well.
Important thing is that
But
this material
without
is
even the
not
magnetic field, they are reporting this value of 15%. So after they tried with in-plane magnetic field to align the thing, but yeah, that's it.
And this is what is done in strontium ruthenate 327. They put an in-plane component of the magnetic field, and then they get essentially a single domain. And then they can rotate the domain, and that's the nematic state in 327 is that. So that's why when I saw that, I said, well, this is nematicity that you're looking at.
Yeah,
Till
we
now,
have to do other
yes.
experiments to see that.
Yes.
Right.
But you can do experiment where you track the transition temperature of the magnetic order. Then you can, if it coincides, then it's quite good evidence that it's probably magnetic.
Right.
And also in strontium ruthenate, wasn't it metamagnetic transition? They really needed magnetic.
Well, that was, or the original idea was the metamagnetism. What they actually saw was nematicity. Before so they saw this metamagnetic transition, but it was actually suppressed by a nematic phase.
But the origin was attributed to non-magnetic.
Well,
This is
the
not a-
origin, the mechanism is a different story. Okay, that's the question. This is a different question.
So, I mean, my comment to Eduardo is, when you see that, you see nematicity. When I see P wave. So then we have to find something else that can distinguish between the two.
Wait, that's because that's quadrupolar. It's not dipolar.
Yeah, but that's a consequence of having P wave too. So that will come together with a P wave. So essentially now we have to figure out which of the two, a very specific experiment as we'll talk about now, that will distinguish.
In fact, it's a record in our spintronics community.
Okay.
Okay. So far for this material, we have obtained the non-relativistic resistive anisotropy that is coming solely from this exchange-driven mechanism. So the next is we compare how our P wave spin polarization, I will not call it a spin texture, comparable with this relativistic Rashba spin texture. Like it breaks for both of the case, the inversion symmetry is broken, the time reversal symmetry effective is preserved. But the difference is that for the relativistic Rashba systems, the spin texture is isotropic in momentum space, whereas this P wave, nodal P wave coplanar one for this example is anisotropic in nature, like the magnitude of the spins are changing with momentum. And the contrast is that for the relativistic Rashba systems, the spin texture is only in plane, whereas we have seen for this coplanar P wave systems, this spin polarization is out of plane. So there are similarities and there are differences also. So we know for the relativistic Rashba systems, so we can have highly efficient charge to spin or spin to charge conversion. Like if we apply an electric field, like in the plane, it shifts the Fermi energy, and as a result, there is an non-equilibrium between the spin up and the spin down channel, and as a result, we are getting an net spin accumulation. Like with the charge current, we are getting transverse spin current accumulation. Can we get something similar for this non-relativistic P wave magnets or not? That's the question. We answer it now. Of course, we will get it because if we apply electric field, the naive idea will be it will shift the Fermi energy, and as a result, it will accumulate the spins, but the spin accumulation will be out of plane. So, for this calculation, we chose the similar same material CaNiAsO, and as we do for our generic mechanism, first we do the symmetry analysis and check what are the components of the susceptibility, Edelstein susceptibility tensor will be surviving, and we see that Zx and Zz component will survive. The Z, the first index is coming from the spin and the second index is coming from the velocity, as clear from this expression of this delta x, and chi is defined as the spin accumulation divided by the applied electric field. So, we see the Z in our calculation also, the realistic calculations done from first principle and after post processing course, like Zx and Zz component survives. Now, for this cerium nickel arsenic oxide, cerium is a 5D element. So, in general we expect the spin orbit coupling effects will be very much pronounced. That means, with exchange driven physics, there will be spin orbit coupling driven physics also. So, for that we now moved to adding spin orbit coupling into our calculation. That means, spin orbit coupling will break some additional symmetries, and as a result we are getting some in plane component of the susceptibility tensor here. Although the in plane components are very much allowed, still the subdominant or the pronounced one is coming from the exchange driven physics. And to put that from this curve, I think nothing is clear how like big or how small is this, rather than which one is finite and which one is not. So, to put that into perspective, now we compare with the relativistic Rashba spin orbit coupling and with some non-collinear systems for which the Edelstein response is reported, which makes both inversion and time reversal, which are not necessarily the p-wave candidates, and our system. So, for the relativistic Rashba systems, the chi s is reported to be 0.36 h bar angstrom by V with this unit, and for this non-relativistic non-collinear systems which breaks both P and T has very similar value with this Rashba systems that has been reported. Whereas, when we calculate for one of the candidates of this P-wave magnets, it surpasses at least 25 times whatever reported till date. So, it is a huge. So, yes.
No, in the previous slide, you didn't.
Yeah, this units are different because this is density, and when I am reporting that this for a system, when I am reporting it's with the volume.
But like, let me just ask you this: when you include the spin orbit coupling, do you understand why it goes down so much?
Like not always, like.
No, on the right side where you had the highest value. Yes.
The spin orbit coupling thing, we need to see the band structure, how it changes the relativistic band structure. There, if the Sx and Sy component are subdominant, like or the pronounced than the Sz component, so then it can be expected that it will reduce the exchange driven thing, the non-relativistic one, because without spin orbit coupling, as we see with the coplanar symmetry, the Sx and Sy components were not allowed. But when we calculate with spin orbit coupling, where the magnetic symmetries are our like things to notice, if the Sx that bands contribute primarily Sx and Sy components, that will be huge response for that we see it here, like where this Sz components dominates, they are the Sx and Sy components has a very low value.
The X, Y, Y, which will be 0, raises a lot at that stage.
Okay. Yeah, because if you see the, without that, this like without spin orbit coupling, any of the in-plane components were not allowed. And now the question that I raised at the very beginning, why I am interested to coplanar systems, not the non-collinear, non-coplanar systems. Because if you see, here we can essentially distinguish which components are coming from the exchange physics and which components are essentially coming from the spin orbit coupling driven physics. So that's the beauty of this coplanar magnets. It gives exchange driven out of plane order, whereas this spin orbit coupling driven mechanism gives you in plane thing. So wherever the mechanism, how you measure it, you can tell how pronounced is the non-relativistic effect and how you can separate it out. That's why we are interested in this coplanar thing, because with non-coplanar, as Anna has done already some calculations, if it gives you the in-plane texture. So there you can't distinguish between, in some mechanism you may do, but you can't apparently see that which one is coming from relativistic origin and which one is coming from in experiments. So now, yeah, I have cheated one thing. Nobody noticed that this gamma is actually my scattering parameter, which is system dependent. When I am comparing two systems, how can I get this scattering parameter? How I am like, I can choose same scattering parameter for both the system, but it can be different, right? Depending on that, these values may change.
You mean scattering parameter is the conductivity?
You know. You know. That's what I'm trying to say. It's not happening.
Now, Rafael, you are beaten. Cairo scholar was today more brutal.
Sorry.
That's the only surprise I could give, because the P-wave magnet out of plane.
Mea culpa, mea culpa.
Yeah, go. Wow.
Yeah, that's I had already said. So we have.
We didn't hear.
So we have compared a quantity which is scattering time independent. Like we take the Drude conductivity, which is also dependent on the like linearly on scattering time, and as well as our susceptibility. And when this ratio is giving me some difference, then it's something to notice. Like here we have reported for the P-wave candidate, and here so far I have found the highest value of this Edelstein response for this non-collinear magnets which breaks P and T both. And you can see from this scale itself that how much large is this, like this chi by D ratio. It's like around 500. Even here I have zoomed in, it's like 50 to 100, and here it's like of the order of 10. So far we have figured out two spintronics or response characteristics that can be useful for spintronics applications. One is exchange driven resistive anisotropy, and the second is the Edelstein response, which is very much different from what we expect in the Rashba systems, the out of plane Edelstein response. And here I conclude, we figured out like there are materials, many for this P-wave candidates, which can have both nodal and nodeless characteristics, and it can give rise to giant anisotropic conductance, which has nothing to do with, in principle, with spin orbit coupling. Spin orbit coupling can give additional effects, but it's coming from the exchange physics, and it can have giant non-relativistic Edelstein effect that can be essentially experimentally we can figure out which is the exchange driven or non-relativistic one and which is the relativistic one. So that's the thing I need to do.
I'll come back to this issue. Is it known if the temperature, if the anisotropy is temperature dependent, and how does it depend on temperature?
Magnetic ordering
No, the measurement for the transport anisotropy.
I have to check. I don't see in in their paper.
I mean, if this is related to some ordering effect, I will expect that to have a more or less sharply defined onset temperature. Okay.
But
I haven't
no,
looked at those papers.
it's just this month.
I mean, I have to warn you,
But I have not seen in their paper.
that most nematicity in electronic systems is usually doesn't have a really, doesn't have a classic square root singularity, but it has more like a foot. okay, for reasons that are not entirely clear, okay, at least in experiment.
Yeah, probably all P-wave.
Well, I don't know.
They have to do Einstein. Yeah.
Thank you very much for this very nice talk. You put your results very nicely in the context of spintronics. I personally do not know any cerium-3 plus oxide compound which has a Curie temperature higher than 15 Kelvin. So I'm wondering two things. Whether you have an idea how to increase the Curie temperature, or whether you want to put this into a context of cryospintronics together with superconductivity or something else.
That's something I have not yet thought about, but yeah, that can be a discussion of the future.
Okay.
But yeah.
So the reason is that we have 70 materials and we have chosen this one just because we already... No, we didn't care at that point about the application, so we just had that material one-air functions.
No, one condition is this was metal.
We have materials which have at room temperature.
And also the metallicity.
Yeah.
Thanks for the great talk, Atasi. At some point you were comparing values to numbers of lutetium ferrite, this perovskite, and I was wondering...
Yeah.
That's the hexagonal version, right? Not the orthorhombic one.
This is the hexagonal version. I can go it.
Right,
I
okay.
have put the structure. This is.
Oh, I see. Okay, yeah, perfect. Thanks.
Thanks for the talk. So, if I understand correctly, it's basically Edelstein effect is just like a spin resolved through the conductivity. It's a spin resolved through the conductivity, right?
For Drude conductivity, you have two velocities. It's like one spin and one velocity.
It's not a polarized current, it's a spin accumulation.
But that would be two velocities is Kubo.
No, it's one spin and one velocity.
So it's Drude.
You run a current and you get a spin accumulation, a spin, not the polarized. This is not a polarized current.
Yeah, but that's the question basically. How would I measure it experimentally in an experimental setup?
From a spin accumulation from MOOC, this is done all the time in the spintronics. You can actually have you inject that spin accumulation somewhere else from spin diffusion. So that's measurable.
Yeah, but
our community we do that all the time. It's actually been observed in 2D in semiconductors.
So you apply a voltage and you measure the spin accumulation. Okay.
Essentially, it's like a non-equilibrium magnetization that you run a current and it's linear in the current. Yeah.
And you can also put a ferromagnetic layer on top and check how the spin accumulation percolated and give you spin orbit torques.
So thank you very much, Atasi. Very nice talk. Going back into the literature, this system has been discussed very much in the context of Kondo lattice and hybridization between the moments of cerium with the 3D electrons. What can you say here? Because now we are moving this into the context of alta magnetism. Can you say something about the Kondo physics? Because even there are works that they claim to have measured a Kondo temperature and all these effects of Kondo physics. So how are we bringing now this together? I mean, I think it's very nice to just extend that also to this Kondo, where you have hybridization between these two sublattices.
Kondo physics would be much lower temperature.
It's at lower temperatures, indeed, because you are now at, I think you are...
The transport is much higher.
So at which, that's a good, the good point is here, the temperatures you are here thinking of, it's above, let's say, 20K. Because Kondo comes in about 5K or something like that.
Then it will be completely different, much suppressed the moment of this. So it's not even this kind.
Okay, so you are always talking about high temperature.
No, this is single particle. No, this is not addressing any Kondo physics. Which by screening, it will reduce it. Sorry, I say because he doesn't know what are they two.
Okay, thank you.
I don't either, but...
Interesting.
Sorry.
You remember during... No, in fact, some of the Kondo guys wrote to us while we published in... Yeah.
Because this is being discussed.
That had a forgot.
So that's why I was... She knows more than you.
Of course. Everybody knows more than me. That's the definition.
Do I understand correctly that the spin polarized currents are forbidden in these materials, right?
The spin accumulation is not spin polarized current.
Yes, but the spin polarized currents are forbidden, aren't they? Or is there a situation where it's possible?
You think that because the time reversal symmetry is preserved?
I think that because you never mentioned that, I assume.
Okay.
Yeah. So it's forbidden, right? Yeah. Right.
What have I studied?
Yeah. So.
I haven't.
Well, you are in a Nature paper that says P wave somewhere.
Oh yes.
Ah, there you go. But it's there you go, even better. Yeah. So the P waves, the pure P waves will have for Jerome's. Where's Jerome? Oh, he's checking his email somewhere. Okay.
We were discussing that already.
So the time reversal is a point group element. Okay, a symmetry of the point group, meaning that any response in this case will be even in time. That's the key. In the helix states, is also odd, but because of the lattice that is underneath. If you just look at the helix state alone, as if nothing else exists, that will be by definition P wave. But because of the lattice, you allow in some breaking of time reversal, so a small component of some of those. But you still will have a fairly strong, as well, in those helix states, Edelstein effect. They're not as big as this one. Okay. But that's another system that you should also explore this physics and may actually have higher temperatures, in fact, and in some of them will be controlled by electric fields, for example, in your cases. So even from a point of view of devices, the helix states can also have a huge potential, something that Naira, for example, had studied in her studies as well, which we saw comparable systems. But there was a bit of a differentiation which you were careful to point out, and when I talked to Ricardo, I said, just go ahead and call it, and the hell with it. Yeah.
I have another point to mention here, like when that time reversals broken helix state, in presence of spin orbit coupling, if you actually calculate the spin projection values, apparently it can be seen like the up and down, like plus and minus for momentum reversal, but the magnitude differs very slightly. That's the basically the time reversal.
The DFT people in that paper, and actually we should name them Sergio. Yes. Pardon? Paolo, sorry.
Yeah.
Paolo, not Sergio. I'm sorry. We are jet lag.
And the lady?
And Silvia Picosa. Yeah. So when they did the calculation, they. Paolo Barone. No, I already said that.
You said Barone. Okay.
No, he said Sergio Barone.
I was thinking of Sergio Leone, but that's a but so when they calculate the spin split, indeed, when you include spin orbit coupling, that it was a tiny difference. That's why.
Yes.
Correct. But they didn't calculate the Edelstein effect, which should be there. So I was curious to know if they calculate that, if it's also going to be a big change.
I just want to show it. If you see this structure, and if you just compare this point and this point, it apparently shows that this opposite momentum are opposite in sign. But they have like calculated the values and they differ, but still their Edelstein response is much more smaller than. But I don't know about this T broken NII2, I think.
That mixing will always reduce.
Right.
Yeah.
I have one further question. At the very beginning of your talk, you excluded deliberately non-coplanar magnets. But in principle, maybe that's my understanding, everything would carry through if you have a non-coplanar magnet with a staggered spin chirality.
The thing why I was not interested in this project to non-coplanar magnets is like it stabilizes or it gives spin projections in the plane. And my interest was like, can we in experiment decouple this exchange driven thing with spin orbit coupling driven thing? Because coplanar magnets, it gives the exchange driven physics to outer plane and the non-relativistic one in the in plane. that we can decouple essentially in the experimental results. And when we see indeed we can do for non-coplanar magnets how it can, the interplay of Rashba and this in-plane texture, what can come up, that's the next idea.
I understand. Okay, thank you very much.
But you even have for the Kagome lattice, you also had.
Yeah, I have.
For the Kagome lattice, you had some calculations.
I have, but that's a model level.
She has model calculations for the situation which you.
Yeah, that's with.
We didn't put it in the story.
That's within the model level, but for this, why we are interested, that's what I tried to say.
I wanted to follow, if I may, still. So I have a question to discussion for Eduardo and Rafael. So in
Explain to them who Sergio Leone was.
so in our community, when you show us rho XX minus rho YY divided by the sum, it's anisotropic magnetoresistance. So you take iron, you have a spin orbit coupling, you have in-plane moments, and for X and Y direction, it's different. Yeah? So is it in your textbook also an example of nematicity?
So,
no, right?
Well, Eduardo and I may have different. I would agree with him. That's okay. We can deal with that later. But what you were referring to, right, is that you have a ferromagnet and the anisotropy or the nematicity comes because of the direction of the moment.
Yeah.
In that case, you're only going to get an anisotropy if you have spin-orbit coupling by definition, right? So some of the nematics we're talking about, the spin is isotropic, like what Eduardo was saying about the iron-based superconductors, is that you have now the wave vectors are related by a 9-degree rotation, but the spin can point in any direction. Then you don't need spin-orbit coupling or anything. I mean, they're both the same. I would call both nematicity because they only tell you how rotational symmetry is broken. They don't care about time reversal. But the mechanism in one case, as you're describing, you need spin-orbit coupling. You need to break time reversal because that's the direction of the moment that is doing that. In most of in the cases that a lot of us work on, it's irrelevant the direction of the moment. You agree with me?
Yeah, I forgot to give you the thing, but you give an explanation without being recorded.
Yeah, that's better, then people can call me.
There you go.
But so, okay, very nice. So I understand. So now when you take the P wave.
No, but the point is that in the absence, I mean, that's why I asked about the temperature dependence.
Yeah.
Because if this actually is an ordering, if the anisotropy is due to an ordering effect, it should have an onset in temperature.
Yeah.
Okay?
Okay.
And if it is due to spin orbit, it will be there forever.
Okay, then we agree. Okay.
So, if I go back to your P wave, actually, the P wave story I think matches very much with what I was saying, and Daniel because I was asking him that, because the anisotropy here. I mean, your spin, right? You said in plane and sigma z, but you don't have spin orbit coupling, right? The spins can point in any direction, any plane, right, that you want. It doesn't need to be the plane x, y, right? So exactly. So, but you have 0 pi, right, which double the unit cell in this direction, or pi 0. So you have two degenerate states, and it is because of that I would claim that you have an anisotropy. It comes from the fact that you have two separate wave vectors, and not because of the direction I'm on. So you should have that without spin-orbit coupling, and that maps, I mean, this is the same kind of material. There is a cerium, iron, arsenic, oxygen as well that people studied that has this pi 0, but the difference there is that the moments are not forming this pattern, but they are collinear.
But we have this also without spin-orbit.
Right, so collinear or non-collinear, if you have 0 pi and pi 0, you need necessarily to get an anisotropy. So that I think that was the point, that just by having the anisotropy, if I had the iron version of that material that doesn't have P wave, they're also going to see an anisotropy. Now I don't know the size, the magnitude, that I cannot tell, but from the symmetry. So I don't know if that answers your question.
Smoking gun would be the anisotropic.
It needs exactly, absolutely.
Because the two can be, he sees nematicity, I see P wave.
And just a follow-up, so for the systems, Rafael, we should just mention in the superconductors.
So for the systems, it's established microscopically what is the mechanism for the anisotropy?
There were two people in this room that, yes, claim, right? Yes. That is, sorry, that have, so in that case, what we believe happens is that, well, it really what happens, okay? But we believe that the nematic is a vestigial phase of the 0 pi 0 order. And in fact, you could have the same vestigial phase in your case because you have pi 0 0 pi order. I don't know if people have ever looked for it, but they should, right? So in that case, then the reason why you get an anisotropy is because you have fluctuations around pi 0 and 0 pi are different in magnitude, so you have different scattering. Yes, exactly, precisely. Yes, exactly. Is that S pi 0? So at finite temperatures, it would be a scattering of magnetic fluctuations that are now unequivalent in both. Now, Brian is here too, and he's already giving me 30 eyes. That he also has, if you have impurities, the impurity will be dressed by this as well. And even at 0 temperature, you'd get the resistivity anisotropy. So the problem with resistivity anisotropy is that you have many mechanisms that can give rise to that. But all ultimately comes from, in my opinion, from this pi 0 0 pi difference that you'd get again.
In most cases, it will not look like an ordering.
No.
Okay, so in this case, it's due to an ordering effect, and that's why the temperature dependence is important.
I think Roger wanted to say
Thanks a lot. Thanks a lot. Thank you.
I'll take it.
Okay.
I just wanted to say about the mechanisms of nematicity that, of course, we have here in the room everybody's of the same school, but depending. Apparently not. No. I'm trying. No. Me too. No, I am in the same school, but I'm just saying that this has been a topic of really a lot of intensive discussions and controversy in the iron-based community, and just. Exactly. I mean, really, with almost not that bad as in the cuprates, but this is so. Just to say, the mechanism we all think is that, but it's not the only explanation or the only scenario. One has to say it and mention it. Okay. That's why. But I just was trying to say that it's solved. I mean, many of the experiments really agree or are consistent with this scenario that basically was being presented. Exactly. That's the point. That there is an outlier. There is an outlier where you have to then do much more explanation. So, but now I'm going to give it to Eduardo, who will have the last word.
Not necessarily the last word. But no, this is why I made a point of discussing a little bit between having a phase with a given symmetry and the mechanism that gives rise to the phase. There may be more than one. So for instance, in the case of, take YBCO, the good old friend, high temperature superconductor, in the very underdoped regime, there is nematicity and it's due to a melted spin density wave or partially melted spin density wave. Okay? If you go to optimal doping, there is essentially no magnetism left. And there is purely due to a weakly formed charge density wave that is essentially melted. That's what people believe, at least. Now, these two regimes, these two phases, are not different from each other. They break the same symmetry. And so in principle, in a phase diagram, they should be continuously connected. So in the case of the iron superconductors, okay, I think there was a fight between people who wanted to say it's orbital ordering and people who say it comes from the spins, and both can be correct at the same time, because the orbital ordering means that an orbital is more occupied than the other one and so on. It's like having valleys, for instance, people call valley anisotropy and all of that. But so there are different mechanisms, but the point is that the phase is characterized by the symmetry that it breaks, not by the mechanism. Okay, right. Okay. Right, but there may be more than one. It may depend on the material, maybe depend on the regime in the same material. So when as you dope, for instance, you may go from one regime to another one, for instance. Okay.
So finally, I want to acknowledge. Always I forgot this.